In this video, we're going to do an example problem where we look at what it would feel like if you stuck your hand under Niagara Falls. So we're going to look at the force on your hand under Niagara Falls. What would it feel like if you took your hand, here's your hand. Apparently you only have 3 fingers, but you lost some in the battles, I guess. And you have water coming down onto your hand and causing a force on your hand. We'll define the down direction as the x direction. We know that the area of your hand is 80 centimeters squared, and the velocity of the water is equal to 30 meters per second near the base of the falls. So this would be 30 meters per second I hat. Okay, so what would be the force on your hand? Well, first look at what our control volume would be. So the first step is to define our CV. And we're going to define our CV based on where the velocity change is actually taking place. So let's look at what that would be a little bit. So we're going to have water that's coming down and going over our hand, something like that. So this is the that's your hand. So water is going to be coming down and flowing around and over that surface. Okay, the control volume is going to be this where this velocity change is actually taking place. So in this case, it's actually a pretty good estimate that it would be this region of space right here as our CV, and we would have 2 surfaces to that. We would have a top surface we'll call 1 and a bottom surface 2, which is down here at the bottom. And then we also have the front, side, and back. We'll call this maybe side 3 and side 4. We'll just look at the left and right side. So we're going to be having water coming in side 1 and leaving side 3 and 4, but exerting a force on your hand, which is side 2. So a little bit tricky to kind of wrap your head around, but we're looking at where this velocity change is actually taking place. So where the water first starts slowing down to where it actually hits your hand and then goes out the side. The equation that we're going to be using for the force is just looking first at the x direction. Again, so our x direction, we defined the same direction as the water is going. If we look at our x direction, our net force in the x direction is equal to dt. This is the full Reynolds transport theorem momentum equation, CV of v velocity, density, velocity dotted with the area. If we want to look at the steady state solution, this whole first term drops out. You'll hear me say this quite a bit, but we're typically in this class only interested in the steady state solution because the time-dependent ones get to be pretty complicated. So we're interested in the steady state solution. If we have steady state and uniform velocity, again, these are going to be common in this class and relatively common in the real world. The net force on our control volume in the x direction is equal to the sum over all of those control surfaces of u, which is the x component of the velocity, times density, times velocity dotted with the area. All right, so what are these specific terms? Well, we're going to have terms for in the x direction. We're crossing in, right, we have velocity crossing in the x direction here at the top surface and at the bottom surface, and not at surface 3 or 4. So we don't actually have to care about 3 and 4 because they're not in the x direction. We don't have velocities in the x direction. We only have to care about surface 1 and 2. So this is going to give us the net force in the x direction equal to, this is u1 rho velocity at surface 1 dotted with the area of surface 1 plus u2 rho v2 dotted with a2. And now we can make an observation, right? So u2 equals 0 because it stopped in x at your hand. Right? It's not going through your hand, it's stopping at your hand. So u2 is 0, so that makes that whole second term cancel out to 0. So the net force in the x direction is equal to the velocity at surface 1 times the density times, again, the dot product of these, which is going to be negative u1 a1. Just to describe how I'm getting that, right? We have a velocity. This is v1 equals the u I hat, and a1 is equal to a1 as a vector is a1 negative I hat because it's the outward normal. So when we do the dot product of those, we get negative u1 a1. They're pointing in different directions. So the net force acting on our control volume is negative u1 squared rho a1. Another way to think about that is, right, this is the force needed to cause the observed fluid acceleration. So that's the force, the net force that needs to be acting on the control volume to cause our observed acceleration, right, this is what forces are acting on our control volume. Well, there's going to be a body force, which is actually the weight of the water in the control volume. We don't really know how big our control volume is, so that's actually hard to know specifically. Our control volume is going to be the area or the volume where velocity is changing. We don't actually know how big that is exactly without doing some more detailed looking at this problem, but we can say that it's going to be relatively small compared to the other forces, compared to the force of the water decelerating or coming to a stop. So this is about equal to, or I guess I'll write it this way. This equals FB plus FB in the x direction plus RX. This is the weight of water in our CV. Which we don't know exactly what it is, but it's relatively small. Then Rx is the force, the other force acting in the x direction is your hand pushing on the CV. So that equals negative U1 squared rho A1. And if we want to put numbers on that, F body force plus your hand pushing Rx equals minus, would be 30 meters per second squared times 1,000 kilograms times the area of your hand, which is, what did we say it was? It was 80 centimeters squared. 80 times 10 to the minus 4 meters squared. We can say that the body force is about equal to 0. We don't know exactly what it is, but it's going to be small. And Rx equals negative 7,200 newtons. So that is a force, again, pushing in the negative x direction, which is pushing up. So this is pushing up on CV. So we need a force of 7,200 newtons pushing up on the CV in order to cause the flow to do what we're telling it to do, in order to cause that acceleration change. Or another way to frame that is the CV / water pushes down on hand with 7,200 newtons of force, right, which is a lot of force. That's equivalent to right, over 700 kilograms of holding up something that's over 700 kilograms. So a very large amount of force. You're not likely to be able to hold out your hand and, you know, keep your hand straight to be able to actually do this. But if you could, Niagara Falls would exert a 7,200 Newton force pushing down on your hand. So hopefully with this example, you see some of the kind of key features of looking at problems like these. As maybe you can tell, really keeping track of what are the net forces acting on our control volume, how we define the control volume itself are challenging and take some practice. We do have you know, specific directions that we're going to be looking at, like the X direction. So things are going to be happening in the Y and Z directions. We're just not looking at them in this case, because we care about forces in the X direction. So we have to really kind of be careful as we go through these problems and be careful with what are our directions, what are our forces, where is our control volume, and what's exactly happening to that. But if we do those things carefully, there are a lot of different types of problems that we can solve, and a lot of different behaviors of fluids that we can begin to understand.